Good morning, students. Welcome back to another Waidsum Academy video. Today we are doing IGCSE Chemistry Chapter 12, Acid, Bases, and Salt. In this chapter, we are going to learn about what are acids and bases. So let's begin. So, question. Why are most organisms not able to live in Lake Natron? The lesser flamingos have a special tough skin on their legs. Suggest how this helps them live in alkaline water of Lake Natron, and suggest why the lake is called natron. Think of a chemical symbol of sodium. Now, Lake Natron, found in northern Tanzania, contains water that is so corrosive it can burn people's skin. The water is corrosive due to the alkalinic substance present. Although the harsh conditions of the lake make it inhabitable for many organisms, the lake is an important breeding site for lesser flamingos as alkaline water keeps most predators away. The high alkalinity of the water is due to the presence of salts such as sodium carbonate and sodium hydrogen carbonate. These salts are found in many cleaning products around us. And because of the flamingos' legs, special tough skin in their legs, the flamingos have the ability to live and breathe in this lake naturally. So let's go to our first section. Section 1. In this chapter, we're going to learn about alkalines and acids. And in section 1, we talk about acids. In this section, we're going to learn about acids that contain the hydrogen ion, H plus ion, and describe the properties of acids in terms of their reactions with metal, base, and carbonates, and also define acids as proton donors. Now, acids. Many natural occurring acids, such as citric acids in oranges, are sometimes known as organic acids. There are many other acids called mineral acids. Most of these are man-made, such as nitric acid and sulfuric acids. So what are acids? Acids are substances that produce a H plus ion when dissolved in water. As aqueous solutions, the H plus ions are responsible for the properties of acids. As I explained, there are two types, organic acids and mineral acids. Organic are natural acids, such as citric acid found in oranges, and mineral acids are man-made acids, such as nitric acid and sulfuric acid. Now in this table, here are a bunch of common acids such as ethanoic acid, hydrochloric acid, nitric acid, and sulfuric acid. Now these are the most common acids that are always shown in your IGCSE chemistry paper, and you will see questions based on them coming up in your IGCSE paper. Now what you should notice that all of them are aqueous and they have the H plus ion, and it's what they produce when mixed in with water. Now they have their own formula which you should memorize. You can pause this video and write them down in your notes, or you can memorize them. Now when they're dissolved in water, they produce H plus ions, and they become when they produce the H plus ions, they give out protons. They were proton donors, and they lose the ions and become negative. That means they gain an electron and become negative. They lose the hydrogen and become negative. So now let's move on. Now if you don't know what the negative is, you can watch our chapter 11 video, chapter 11 IGCSE chemistry video, where we talked about oxides. So now let's move on to what are properties of acids. Now reaction with reactive metals. Acids react with reactive metals to form salt and hydrogen gas. So we should memorize this, as it explains that when you mix in metal and acid, salt and hydrogen is always going to be the products of the reaction. The reactants of metal and acid produce the products such as salt and hydrogen. Now, here's an example: magnesium and dilute sulfuric acid. Magnesium is a metal, while dilute sulfuric acid is a, well, acid. Now, when they mix together, they form magnesium sulfate and hydrogen. Now, in this case, the magnesium sulfate here is the salt, while the hydrogen is, well, hydrogen. This is obvious. As you can see in the reaction, that what happens here is the sulfuric acid gives the dilute sulfuric acid, it throws a hydrogen leaves the dilute sulfuric acid, and the magnesium over here mix in with the sulfur to produce magnesium sulfate, while the hydrogen leaves the dilute sulfuric acid to just be on its own. Now, this is a balance equation explaining of magnesium, the reaction between magnesium and dilute sulfuric acid. Now, magnesium sulfate is the salt produced when magnesium reacts with sulfuric acid. Salts are called sulfates when they form with sulfuric acid, nitrates when they form with nitric acid, and chlorides when they form with hydrochloric acid. So different salts are produced when you react a metal with different acids. Now, this explains that when you react magnesium or any other metal with different types of acids, the type of salt produced is going to be different. The name of the salt is going to be different. Like magnesium is magnesium sulfate only because we reacted it with dilute sulfuric acid. If we were to make magnesium react with nitric acid, it would probably be magnesium nitrate. The salt magnesium nitrate will be produced. If we mix magnesium or any other metal with hydrogen chloride acid, the salt chloride is produced. So now that we understand this, this image shows that the ship body is made of iron, now which corrodes in the presence of oxygen and moisture in the air, which is H2O water. This corrosion is worsened in the presence of acid rain. Now, if we move on, here is testing for hydrogen. We can test for hydrogen gas by placing a lighted splint in the mouth of the test tube. Hydrogen gas extinguishes the lighted splint with a pop sound. So this is a basic chemistry experiment that it's known that in chemistry, if you want to test the gas if it contains hydrogen, you test it by putting a lighted splint in the mouth of the test tube. If the lighted splint makes a pop sound, the hydrogen, it proves that there is hydrogen gas in the test tube. As hydrogen gas, this is something you should know, as hydrogen gas extinguishes the lighted splint with a pop sound. Now, not all metals react with acids to give a salt and hydrogen gas. When we say metals, we should know that not all metals have properties that can allow them to react with acids to produce salt. This is true. Now, when unreactive metals such as copper or silver are added to dilute acids, there are no reaction. Lead appears to not react with dilute hydrochloric acid because the initial reaction between lead and dilute acid produces a layer of lead 2 chloride or lead 2 sulfate. This layer is insoluble in water and quickly forms a coating around the metal. The coating protects the metal from further attack by the acid. Now, an example of why unreactive metals, or why metals can react with acid, is that when they react with acid, an insoluble layer is produced. Like example, in lead, when it's mixed in with dilute hydrochloric acid, a layer of lead 2 chloride is produced around the metal, and this layer is very insoluble, that is, it cannot react with water. This coating protects the metal. Now this coating, it protects the metal from any further attacks of the acid, so the acid and the lead cannot mix together, causing the lead to be unreactive. Concentrated nitric acid reacts with metals but does not give hydrogen gas. Instead, it releases nitrogen. It's nitrogen dioxide. So remember when we say that when metals react with acids, they form two things, salt and hydrogen. But this is not the same. This is not so for nitric acid. When concentrated nitric acid reacts with metals, instead of hydrogen, nitrogen dioxide is produced. So you should also note this down, because it might be a question that is commonly asked in your chemistry Igcse exam. So now let's go to reactions with bases. Metal oxides. The general equation for the reaction of metal oxides with acid is metal oxide plus acid equals salt and water. So instead of hydrogen or nitrogen dioxide, this time metal oxides react with acid to produce water and salt. Example, zinc oxide. Now zinc oxide and diluted sulfuric acid are the reactants in this reaction, and they react together to produce zinc sulfate, which is a salt, and water, which is H2O. As you can see, because why? Because in this equation, if you look, zinc oxide contains oxygen. Oxide is oxygen, and the dilute sulfuric acid has sulfur and hydrogen. Now, in this case, the hydrogen and oxygen react together, and this causes them to form water. And while the zinc and the sulfate react together to the zinc and the sulfur react together to form zinc sulfate. Now this is a important thing you should understand, that when metal oxides react with acid, they form water. But it's different with metal hydroxide. The difference between metal hydroxide and metal oxide is metal hydroxide contains hydrogen. So the word hydro in chemistry refers to hydrogen. Now this metal hydroxide, OH, when it reacts with acid, it forms salt and water, just like the metal oxide. Example, zinc hydroxide with dilute nitric acid this time forms zinc nitrate and water. Now as you can see in the reaction, the zinc nitrate is a salt, while the water is water. And how does this form? Well, the dilute nitric oxide produces two forms of water. As you can see, there's two right in front of the water. It shows that when two oxygen and two hydrogen are here. So for it to happen, we will need 4 hydrogen, because in water, 2 hydrogen molecules mix with 1 oxygen molecule. So since there's 2 here, and the 2 is covering the bracket, that means there is a total of 4 hydrogen and 2 oxygen. This means we can make a total of 2 water molecules. That is why there's a 2 in front of the water. Now when zinc hydroxide mixed in with dilute nitric acid, zinc nitrate is a salt is produced, and water, 2 molecules of water are also produced. So let's move on to reactions with carbonates. Acid reacts with carbonates to form salt, water, and carbon dioxide. The general reaction for carbonates is carbonate plus acid equals to salt plus water plus carbon dioxide. For example, the reaction between calcium carbonate and dilute hydrochloric acid produces calcium chloride, water, and carbon dioxide, as you can see in the show. Now, in calcium carbonate, carbonate means carbon and oxygen, calcium carbonate, and hydrochloric acid. Now, calcium carbonate and hydrochloric acid react together to form these products: calcium chloride, which is a salt, water, which is and water, which is a product, and carbon dioxide, which is a gas. Now, you can see in the reaction that when calcium carbonate form together, the chloride in the hydrochloric acid moves to the calcium carbonate, and the extra oxygen. Now you see calcium carbonate. The carbonate has O3. Now the carbon dioxide is CO2. That means we are left with one extra oxygen. And if you notice, there's two molecules of hydrochloric. That means there are two hydrogens and two chlorines. Now the two chlorines both go to the calcium, forming calcium chloride 2. But we are still left with two extra hydrogen. Now this two extra hydrogen goes to, let me change the color. Now this two extra hydrogen goes to the oxygen. It mixes in with the extra oxygen left in with the carbonate to form H2O, which is water. And the other two oxygen go to carbon to form carbon dioxide. The reason why it's carbon dioxide, because di means two, so carbon dioxide needs two oxygen. So this is how the reaction is formed. Testing for carbon dioxide. There's a test for carbon dioxide. We can test for carbon dioxide gas by bubbling the gas through the lime water. Carbon dioxide forms a white precipitate with lime water. A precipitate refers to an insoluble solid particles produced in a liquid by chemical reactions. Now we move on to understanding what is the role of water in acid. Acids displace their property when dissolved in water. When they dissolve in water, they produce hydrogen ions, H+, only in the water. A hydrogen ion consists of one proton and no electrons and neutrons, and acids are hydrogen ions, proton donors, which is hydrogen ions. When a piece of magnesium ribbon is added to a solution of hydrogen chloride in water, bubbles of hydrogen are produced. However, when a piece of dry magnesium ribbon is added to a solution of hydrogen chloride in an organic solvent without water, there is no reaction. This is because the hydrogen chloride can exist as different types of particles when dissolved in an organic solvent and water. When the hydrogen chloride ionized in the hydrogen ions and chloride ions when dissolved in water, the hydrogen ions produced allow the acid to react with magnesium. That means hydrogen chloride exists as a covalent molecule when dissolved in an organic solvent. It does not ionize to produce hydrogen ions, and since no hydrogen ions are produced, there are no reactions with magnesium, as you can see in the two diagrams, as it shows that the hydrogen ions allow in water, the hydrogen ions are produced, allowing the acid to react with magnesium. When organic solvents, the hydrogen ions are not produced, so there is no reaction with magnesium. As you can see, the hydrogen chloride is an organic solvent and it cannot produce hydrogen ions to allow the magnesium ribbon to react with the acid. Now, but in the water, hydrogen chloride in water, hydrogen ions are produced, so the magnesium ribbon reacts with the acid. And now we move on to the next section, which is section 2. But before we go there, let me say one more thing. Acids display their properties only when they are dissolved in water. This is because acids produce hydrogen ions only in water. A hydrogen ion consists of one proton, remember this, one proton, no electrons and neutrons. This makes acids proton donors. That means they give away proton. Now let's go to base and alkali. Now in this section we'll learn about base as a proton acceptor, and we'll describe neutralization between acid and alkali to produce water, and what are aqueous solutions of alkalis that contain OH negative ions. So what are bases? Let's move on. What are bases? Bases are oxides and hydroxides of metals. They contain either an oxide ion, which is oxygen to they contain either which is O2 negative ion, or hydroxide ion, which is OH negative ion. And here are some common bases that you can see in the diagram that will appear in your Igcse chemistry paper: sodium oxide, zinc oxide, copper 2 oxide, magnesium hydroxide, and aluminium hydroxide. The formula Na2O, Na2O, ZNO, CuO, MgOH2, and LaOH3. Now, what you should know is that what are alkalis? Alkalis are bases that are soluble in water. So remember when we said alkalis and bases? Well, most bases are insoluble in water. For example, copper 2 oxide can not react or dissolve with water. Well, alkalis are bases that can dissolve in water. They are soluble in water. An example, a soluble base is sodium oxide. Sodium oxide is an alkali. Now, in an exam, they might ask you the difference between alkalis and bases. They are not the same. I repeat, they are not the same. All alkalis are not bases. That is not true. Alkalis are bases that can alkalis are bases that are soluble in water, while bases are insoluble in water. Most bases are actually insoluble in water. Now here are some common in this diagram shows common alkalis: sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, and ammonia. Now if you notice, most of them have hydroxide in the alkali section. In the alkali, most of them have hydroxide, where however in the base most of them are just oxide, although we do have a few hydroxide. So let's move on to know what are the properties of bases. Now there are bases. Excuse me. Let me fix that real quick. What are the properties of bases? Bases react with acids to give salt and water. This reaction is known as neutralization. The general equation of reaction is base plus acid gives salt and water. Copper 2 oxide and dilute sulfuric acid gives copper 2 sulfate plus water. The copper 2 oxide has oxygen, while the dilute sulfuric acid has two hydrogen. Now obviously, without looking, you could tell that the hydrogen takes oxygen from the copper to produce water, while the sulfur goes and mixes in with the copper to produce copper 2 sulfate. Now the copper 2 sulfate is the salt in this reaction, and the ionic equation, which is ionic equation, which means that the copper 2 oxide and the hydrogen aqueous, this is hydrogen, this 2 hydrogen is the hydrogen ion from acid. So the copper 2 oxide gains this hydrogen ion, and it causes it to become the copper ion plus water. So let's move on to the reactions of alkali with acids. Now this was just base with acid. Now bases, when heated alkali reacting with acid is also similar, as it will also produce salt and water. Sodium hydroxide mixing with dilute hydrochloric acid to produce sodium chloride plus water. NaOH is a base, is a alkali, while dilute hydrochloric acid is a acid. So these reactions are known as neutralization. In neutralization ions, the hydrogen ions from the acid and the hydroxide ions from the alkali react together to form water, and this is known as this reaction. H plus hydrogen ion plus OH negative gives water, as the two H combine to form H2O. This is the ionic equation for any neutralization reaction. So reactions with ammonium salts. Bases, when heated with ammonium salts, give ammonia gas. The general equation for this reaction is base plus ammonium salt gives salt plus water and ammonia. This is obvious because the salt contains ammonium. It's known as ammonium salt. So there's ammonia in the salt. And when it's reacted with base, it gives salt, water, and ammonia. Example, calcium oxide plus ammonium chloride gives calcium chloride plus water and ammonia. Aqueous ammonia is in an alkali. This is because when ammonia dissolves with water, hydroxide ions are formed. The water has been deprotonated to form hydroxide. Ammonium gases can be recognized by its characteristic pungent smell. You can test for ammonia gas with a piece of moist red litmus paper. Ammonia gas turns the moist red litmus paper blue. As you can see, it turns this moist, when here's the liquid ammonia or base plus ammonium salt. When you add litmus paper, it turns the red litmus paper blue. Now, alkalis are proton receptors. It is the transfer of protons that causes neutralization. As you can see, here is a OH. It needs one more hydrogen to form water. So it gains the hydrogen ion from the acid to react together to form water. Let's move on to work example. Here are work example. Identify the products formed when each of the following pairs of substances reacts: copper 2 oxide and ethanoic acid, magnesium oxide and sulfuric acid, sodium oxide and water, and potassium hydroxide and hydrochloric acid. Now this one, copper 2 oxide and ethanoic acid, copper 2 oxide and ethanoic acid forms copper 2 ethanoid and water. This is salt and water. I'm sorry, give me a second. Magnesium oxide and sulfuric acid will give magnesium sulfate and water, as you can tell, because the magnesium mixed with the sulfate, and anything with oxide forms water. Sodium oxide and water forms sodium hydroxide. Why? Because the sodium oxide gains extra H from the water to form sodium hydroxide. Potassium hydroxide and hydrochloric acid forms potassium chloride and water. Why? Because remember, both hydroxide and oxide can form to give salt and water. Now let's move on. Oh, sorry, excuse me. My board is kind of laggy. Okay, 6. Now let's move on to the strength of acids. Here in this section, we're going to learn about strong acid and weak acid. Now, what do we mean by term of strength? What do we mean by strength of acid? The term strength refers to how easily an acid or an alkali dissociates when dissolved in water. Remember when we say when acid reacts with water, they form hydrogen ions? Well, the term strength means that how quickly an acid can form hydrogen ions when reacted with water. Now, what is a strong acid? A strong acid is an acid that is completely dissociates in aqueous solutions. That means when you add the acid into the water, all of the acid molecules will dissociate in an aqueous solution. Example is hydrochloric acid. Hydrochloric acid, when reacted with water, all of the molecules would dissociate in the aqueous solution, producing hydrogen ion. So then, knowing this will make us understand that in a weak acid, only some of the molecules is partially dissociated. That means that not all of the molecules dissociate in a dissociate in a aqueous solution. A weak acid is an acid that can only partially dissociate in an aqueous solution. That means ethanoic acid is an example of a weak acid. Only some of its molecules will dissociate in aqueous solution. Now let's move on to its strength of an acid related to its concentration. It is important to not confuse the strength of an acid with the concentration of an acid. Yes, strength and concentration of an acid is different. A strong and weak refers to the extent of dissociation of an acid, while concentration and dilute tell us how much of an acid is dissolved in the solution. In a solution, some of the acid can be mixed in with different types of other molecules or elements. So concentration explains how much of the acid molecules are in the solution, and dilute means that there's too little of the molecules in the solution. So concentration and strength of an acid can mean two different things. Now let's move on to the next section of this chapter, which is the pH scale. In this section, we are going to learn about the hydrogen ion concentration, neutrality, relative acidity, and relative alkalinity using universal indicator pair. Here we're going to learn about the pH. And this is This is personally a very interesting section in this chapter, and it's one of my favorites in this chapter. Here we're going to learn about the pH scale. Now, what is the relationship between pH and concentration of hydrogen ions? The pH scale is a set of numbers from 0 to 14 that is used to indicate whether a solution is more acidic, neutral, or alkaline. Neutral means that it's safe to drink. It's not too alkaline and it's not too acidic. Like water. Water is safe to drink as it is not too dangerous. When something is acidic or alkaline, it can dissolve or dissociate in our solution, and this can bring harm to our body. So neutral means that it's not too acidic or not alkaline like water. Now the pH scale is there to tell us whether a solution is acidic, neutral, or alkaline, and it's in range of numbers from 0 to 14. Now in this diagram, I don't know if you can see the text, if it's clear, but you can notice that 0 means that it's more acidic. More acidic. While numbers that are higher, close to 14, is more alkalinic. More alkaline. Now, and just right in between 0 and 14, at 7, we have neutral. Now, if you haven't figured it out yet, this pH scale explains how acidic or alkalinic a solution can be. Meaning that if a solution were like to say having a pH of 2, we say that that solution is acidic. And if we say the solution has a pH of 12, we say that it's alkalinic. Now, the lesser the number the solution has, the more acidic it becomes, with 0 being the most acidic. While the higher the solution is, the more alkalinic it is, making with 14 being the highest of alkalinic. Now you can see in 7 we have water. And with 0, we have liquid in car battery, because the liquid in car batteries are very acidic. Then in 1, we have gastric juice in stomach. In our stomach, we have a gastric juice that is actually acidic, allows us to digest food and dissolves them into small pieces. Lemon juice is in number 2. It's acidic but not too acidic, and it's safe to drink. But vinegar is in number 3, tomato in number 4, and black coffee in number 5. All these, and milk in number 6, all these are considered acidic. But if you notice, the higher the more as numbers increases and goes by, the less acidic the solution becomes. Then we have 7, which is pure water. This water means that it's not acidic or alkalinic at all. Then we have 8, toothpaste, which is somehow alkalinic, baking soda, soap, aqueous ammonia, and the number increases, it becomes more alkalinic. Bleach is very alkalinic, as it's dangerous to touch and leave impure skin. Oven cleaner, and then we have drain cleaner being with the most alkalinic. Drain cleaners are what you put in your drains when you have a blockage. So how is the pH of a solution determined? The pH value of a solution can be determined using indicators. Indicators are dyes or mixtures of dyes which change in color when acid or alkalines are added to them. Besides the universal indicator, we can also use other indicators to determine if a solution is acidic or alkalinic. Now here you can see that here's the universal indicator paper, the color chart, and here you can tell that in the color chart you can see that the universal paper can change color depending on whether acid or alkaline is added to it. An example, you have different indicators: litmus, thymophosphatine, and methyl orange. There's many more indicators, but for your IGCSE level, you're only going to learn about these 3. Now litmus, this is a table that you should memorize. In litmus, in an acidic solution, when you add litmus paper to an acidic solution, the color turns red. That means that when you add litmus paper to an acidic solution, it becomes red. While when you add it to an alkaline solution, it becomes blue. In thymophosphatine, sorry, my pronunciation is kind of bad. And this is the thymophosphatine. When you add it to acidic, it becomes colorless, means see-through. It doesn't have a color when you add it to acidic solution. But if we were to add it to alkalinic solution, you'll get blue. And finally, in methyl orange, when you add methyl orange to an acidic solution, it turns red. However, in alkalinic solution, it turns yellow. Now these indicators help us know if a solution is acidic and alkaline or alkalinic. So now let's move on to our next section. But you should also know that, as I just said, there are many other universal indicators like these ones. Universal indicators use colors to tell us if it's more acidic or alkalinic. Or we have different indicators like papers, like litmus paper, or solutions that help us tell us. Some common indicators are thymophosphatine, and methyl orange. So now that we've known that, let's move to our next section, which is chapter 12.5, which is oxides. In this section, we're going to learn about classifying oxide as acidic or basic based on their metallic or non-metallic character. We're going to describe what amphoteric oxides are. We're going to describe what amphoteric oxides are. We're going to describe what amphoteric acids are. So let's move on. Excuse me, this mouse board is kind of like oxides. We're going to start with acidic oxide. Oxides can be 2 things: an acidic oxide or a basic oxide. Now, what are acidic oxide? Many acids and alkalines are formed when dissolving oxide in water. An oxide is a compound of oxygen or another element. Most oxides can be grouped into three categories: acidic, basic, and amphoteric. So what are acidic oxides? Most oxides of non-metals are acidic. That means most of the non-metal oxides, most of the oxides of non-metals are acidic. Most acid oxides dissolve in water to form acids. One example is sulfur dioxide, which dissolves readily in water to form sulfurous acid. Now, as you can see, carbonated drinks are slightly acidic due to the carbon dioxide dissolved in them. The carbon dioxide is added to give the fizz to the drinks. Fizz is the gas that readily moves through and escapes from the drink. Now, there are many non-metals oxides that tend to be acidic oxides that can react to water to form acids. And here you can see that in this table, there's some of the name of these are missing. Let me write them down. Here we have carbon dioxide. Carbon dioxide is an carbon dioxide. Sorry, don't mind my handwriting. Board is lagging. Carbon dioxide is a type of acidic oxide. Here it says sulfur trioxide. Sulfur trioxide. As you can, I'm using because of the formula, I can tell which acidic oxide. There's sulfur trioxide, which is a gas. It can produce an acid produced in water, which is sulfuric acid. And carbon dioxide, when mixed with water, can produce carbonic acid. And the final one is phosphorus V-oxide. Phosphorus V-oxide means phosphorus 5 oxide. This phosphorus V-oxide. Don't mind my handwriting. So we have carbon dioxide, sulfur trioxide, and phosphorus 5 oxide. Now, phosphorus 5 oxide is also an acidic oxide, but unlike carbon and sulfur dioxide, phosphorus oxide is a solid, but at the same time, it still produces phosphoric acid. So let me write the formula of these acids. We have H2CO3. You notice that these two of the hydrogen and one extra oxygen, it comes from the water. When you add water to carbon dioxide, they form together to produce H2CO3. That is why it has 3 oxygens instead of 2, and there's two hydrogen in the formula. And sulfuric acid is the same as you say sulfuric acid H2SO4. Why there's 4 oxygen instead of 3? Because it was originally sulfur trioxide. Tri means 3, that means it already had 3 oxygen. Or when you get an extra oxygen from the water, it becomes 4 oxygen. 4 oxygen. That's why it becomes H2SO4. And phosphoric acid becomes H3PO4. Now this one is also quite clear, as I explained. The 2 of the hydrogen come from the water, and one of the oxygen came from the water. So let's move on to explain acidic oxides. Continued. Now acidic oxides do not react with acids, they do not react with acids at all. They react with water and alkalines to form salt and water as shown. The sulfur dioxide reacts with sodium hydroxide. Now this is an alkali, and it reacts together to form a salt and water. And here are the formulas. Another example is carbon dioxide and sodium hydroxide, which reacts together to form salt and water. So you should know that acidic oxides can react with alkalis to form salt and water as shown. Now silicon dioxide. Silicon dioxide is a solid at room temperature. It does not dissolve in water but reacts with hot concentrated sodium hydroxide to form sodium silicate, which is a salt. So silicon dioxide despite being an acidic oxide, cannot react with water because it's a solid at room temperature. But it can react with sodium hydroxide, which is a alkaline, and they react together to form sodium silicate and water. Hence, silicon dioxide is an acidic oxide. So now let's move on quickly to what are basic oxides. Basic oxide, most oxides of metals are basic oxides, since non-metals form acidic oxides. Metals form basic oxide. Now again, the table is missing some of the text, but I can write this. This is a copper oxide. Copper is a metal. As you notice, copper is a metal. So when it forms, it becomes a basic oxide. Copper oxide. And it reacts together. Here is calcium oxide. Basic oxides are solid at room temperature, unlike the nonmetals, which had gas at physical state. Here, at room temperature, they are solids. That means they react with acids to form salt and water, as shown. Now, just like the acidic oxide, basic oxide can react with acids to form salt and water. But basic to form salt and water. So you can see in this image, magnesium oxide is found in dietary supplements that help prevent low levels of magnesium in the blood. So let's move on to explain what are amphoteric oxides. Amphoteric oxides are metallic oxides that react with both acids and bases to form salt and water. That means they are metallic oxides that form with both acids and base to form salt and water. That means they can react with both acids and base. Acids can only react with base, and base could only react with acids, but amphoteric can react with both of them. So examples of amphoteric oxides is zinc, aluminium, and lead 2 oxide. Now, zinc oxide is used in some lotions and creams against sunburn as it absorbs ultraviolet light. So, the amphoteric oxide, have the ability to react with both acids and bases. Now, the following shows the reaction between zinc oxide and aluminium oxide with hydrochloric oxide. Here are some following. Hydrochloric acid react with zinc oxide. The hydrochloric acid is an acid, and zinc oxide reacts with this acid to form zinc chloride and water. This is the first reaction. As you can see, the hydrochloric acid and the 2 hydrogen of the hydrochloric acid reacts with the oxygen that the zinc oxide has to form water, while the zinc reacts together with the chloride to form zinc chloride, which is the salt and water. Now, the same zinc oxide can also react with a alkali or a base to form also salt and water. Sodium hydroxide is a alkaline, and it reacts together with zinc oxide to form sodium zincate and water. And the sodium zincate is the salt, and the water is all water. And you notice that the zinc in this case, since there's 2, that means there's 2 amounts of hydrogen, and the hydrogen react together to form. If hydrogen react together with the 2 hydrogen react together with the zinc to form hydrogen water, while the zinc reacts with the Na, since there's 2 Na sodium to form sodium zincate. Now the oxygen in the zinc does not leave, as there's already enough of the water, enough for it to produce water. Now, there are many other formulas that you can use to pause and understand as I explain. In reaction to 1 and 3, zinc oxide and aluminium oxide behave as basic acids. However, oxides. in reactions 2 and 4, they behave as oxidic oxide. In all of the reactions, in all of the reactions, salt and water are formed. So let's move on to how can we classify an oxide. So this is very simple. We just have to answer the questions. If you find a sample of an oxide, how would you tell if it's a basic, acidic, or amphoteric? You can do this by asking questions and doing reactions with it. Now the ono acid, does it react with the ono oxide? Does it react with acid? If no, that means this is an acidic oxide. Why? Because acidic oxide can't react with acids. They can only react with base or amphoteric oxides can only react with base to form salt and water. Now, if yes, there's a chance it could be a basic or amphoteric. But how do we tell from there? Does the oxide react with alkali? This is the second question you should ask. If no, that means it's an basic oxide. Why? Because basic oxide cannot react with alkali. They can only react with acid. But if yes, it can also react with basic oxide. It's an amphoteric oxide. And amphoteric oxides, why? Because amphoteric oxides are oxides that can react with both base and alkali. So now let's move on to the second final section, salts. If you notice, salt is a very common product in reactions with oxides, acids, metals, and so on. In this section, we're going to understand what are salts and determine the term water crystallization, and describe the general solubility rules for salts. Now, salts are ionic compounds. All salts are ionic compounds. This means they contain either calcium, which is a positive ion, or anion, which is a negative ion. Salts can be formed by reacting acids with alkali, metals, and excess insoluble bases or excess insoluble carbonates. That means they can be formed if they're mixed with acid and alkali, acid and metals, acid and insoluble base, acid and insoluble carbonate. They form salt. Salt, if you notice, salt is a common product with all these reactions, as salt is always going to be producing these reactions. Water is sometimes producing some of them, and hydrogen gas is only produced in a few of them. Now, during reaction, only one or more hydrogen ions can be acid is replaced with a metallic ion or a ammonium ion. For example, the salt potassium chloride is formed when the reaction above, which is this reaction, the hydrogen ion of the acid is replaced by the metal ion or the potassium hydroxide. K plus comes from the base KOH, while Cl negative comes from the hydrochloric CHCl. The anion of the salt usually comes from an acid, but cation can only come from a metal carbonate, base, or alkali. And remember, since metals can form basic oxides, this is why a cation, which is a positive ion, can come from a metal carbonate or base or alkali. Now, let's move on to salts made from acid, alkali, metals, and insoluble salts. And this is complicated, but you will also need to memorize this if you want to understand the topic. Now, alkali, metal, insoluble salts, insoluble carbonates provides calcium, acid provides anion, and the salt is for potassium hydroxide, aqueous ammonia, zinc, magnesium oxide, and copper carbonate. Now, if you notice, all these alkali, metal, or insoluble base provides the calcium, and the acid provides the anion, which is a negative ion. Remember, a negative means a negative ion. And since you know that ions are negative ion, you will automatically know that a cation is a positive ion. Now, this acid provides the anion that reacts together to form the potassium the salts produced.
like potassium phosphate or ammonium sulfate. Now, what are hydrated and anhydrous salts? Many salts combine when water molecules to form crystal are hydrated salts. They have a regular shape. Now, salts that actually chemically combine with water are called hydrated salts. When hydrated salts are heated, water is given out. The salts that do not contain water are called anhydrous salts. Anhydrous salts are often in powder form. Now, hydrated salts can be obtained when anhydrous salt is mixed in with water. Now, as shown in the diagram, you can see that blue crystals, hydrated copper 2 sulfate, is a hydrated salt. Now, when you heat it up, it forms a white powder, which is anhydrous copper 2 sulfate. This means there is no water anymore, and you can only hydrate it back by adding water in it. So those are what are hydrated and anhydrous salts. Now, what is water crystallization? The water molecules that are presented in hydrated salts are called water crystallization. Copper 2 sulfate, magnesium sulfate, sodium cyanate, and zinc sulfate. Now, the water molecules that are presented in the hydrated salt are called, remember, water crystallization. Therefore, these examples are shown on the table. The amount of water crystallized in a hydrated salt is often known is indicated after the dot in its chemical formula. Now here it shows in the table. Now I don't think it's too clear to see. Well, after the formula or the name of the salt, there is a dot, and a dot to show water. 5 water, 7 water, 10 water, and another 7 water. This does not show the amount of water. These numbers of water are actually known as water crystallization, and it shows the amount of water molecules that are present in the hydrated salt called water crystallization. Now, which salts are soluble and which salts are insoluble? The solubility of a salt must be determined before we can choose a suitable method of determining the salts. Although salts are ionic compounds, not all salts are soluble in water. The solubility of salts must be determined before we can choose a suitable method or for preparing the salt, because difference for making salt on solubilities of what. So how do we have rules? We have rules first for the solubility of salt, and how do we figure it out? By following these rules. So the solubility rules of salts is all sodium salts are soluble, all potassium salts are soluble, all ammonium salts are soluble, all nitrate salts are soluble. All chloride salts are soluble except silver chloride and lead 2 chloride. And all sulfate salts are soluble except barium sulfate, lead sulfate, calcium sulfate, and which is spiraling soluble. And all carbonates are insoluble except sodium carbonate, potassium carbonate, and ammonium carbonate. And these are the rules of solubility of salts that can help you understand the solubility of salt when producing salts. So now we go to the final section of this chapter, which is preparation of salts. In this chapter, we're going to learn how we can prepare, separate, and purify all the soluble salts using suitable methods, and also learn how insoluble salts are prepared. Now, this diagram is a bit blurry, but I can explain what the diagram means. So, salts can be found in many things around us. Some salts occur naturally, while others are man-made. How can we prepare salts in the laboratory? There are several ways to make salts. Before deciding on how to prepare salts, 2 factors must be considered. Is the salt to be prepared soluble in water, and are the starting materials soluble in water? If a salt is soluble, it is usually prepared from the reaction with acid. If the salt is insoluble, it's usually prepared by the preparation method. Preparation of salt. Is the salt to be prepared soluble in water? If it's yes, then reaction with an acid or reaction of an acid with a metal base or carbonate. If no, if the salt isn't to be prepared with soluble water, we use precipitation. Precipitation, solution containing cation of the salt and solution containing anion of the salt. Now, what if the salt to be prepared is soluble in water and is yes? We'll ask the second question. Are both the starting materials soluble in soluble water? If yes, we use the method of titration, which is acid and alkali soluble base, or acid plus soluble carbonate, which crystallize the salt solution, or filter it to obtain the salt of crystals. If not both of the starting materials are soluble in water, reaction of acid with an insoluble substance is used, which is acid plus excess metal, or acid plus insoluble base, or acid plus excess insoluble carbonate. We filter the mixture, collect the filtrate, crystallize the filtrate, and the filter to obtain the crystals. And at the end, using different methods of preparing salt, we will end up with salt crystals. Now, how is soluble salt prepared by titration? The general equations of preparation of salt titrations is shown. In the titration method, all the starting materials are soluble. If any of the starting materials is in excess, it cannot be removed from the salt solution by filtration. Thus, the salt produced will be impure. Therefore, the volume of each starting material used must be exact. The following shows the procedure of making sodium nitrate from the reaction of dilute nitric acid with aqueous sodium hydroxide. Now, we're going to explain the next part, which is how is a soluble salt prepared by reacting an acid with a metal, insoluble salt or insoluble carbonate. The general equations for reacting an acid with a metal, an insoluble metal or carbonate, are here the following. Acid plus metal gives salt plus hydrogen gas. Acid plus insoluble base gives salt plus water, and acid plus insoluble carbonate gives salt, water, and carbon dioxide. Now, in this method, the metal base or carbonate must be excess so that all of the acid is used up and it's insoluble in water. Now, the suitability of metals for preparing the preparation of salt. The suitability. Now, this method used in the let's investigate in 12b, which is only shown in your textbook, is suitable for moderately reactive metals. But, however, it is not suitable for very reactive metals such as potassium, sodium, and calcium, which are all in the reactivity series. These metals react very violently with acid, so the reaction is very dangerous. Unreactive metals like copper and silver, which is also in the reactivity series. These metals do not react with dilute acids. When the metal is too reactive or unreactive, we can prepare the salt by replacing an acid with the insoluble base or carbonate instead. The apparatus and the procedure is used similar and shown in Let's Investigate 12.b, which is only shown in your textbook, but I can do and explain. They say that in step 1, we first fill a half beaker with dilute sulfuric acid with constant stirring. That means they stir here the dilute sulfuric acid is an acid. They stir the acid constantly. Dilute means that it's low concentrated, because concentrated sulfuric acid is dangerous in laboratory. So we use dilute instead. So then when constant stirring, they add the powder, zinc powder, or just say metal powder. Now they add the zinc powder to it while constantly stirring until no more reaction occurs with the acid or no more effervescence is observed. So that means when they add the powder to the acid while constantly stirring, effervescence is occurred. It is the release of gas bubbles due to the chemical reaction in the liquid. Now they filter it. When they are done in step 1, they filter it using a filter paper and a filter funnel. Now in there, the aqueous zinc sulfate is filtered to give aqueous zinc sulfate and excess zinc metals that could not react in the reaction. Then it is the aqueous zinc sulfate is then heated until it's saturated, allowing the saturated solution to cool so that the salt can crystallize. So then it produces saturated aqueous zinc sulfate, and zinc sulfate crystals are slowly forming. Filter to collect the crystals, then wash the crystals with a cold water to remove impurities. Dry the crystals between a few sheets of crystal paper, and then you will be left with zinc sulfate crystals, which are pure. So let's move on to preparing salt with reacting an acid with an insoluble base. Now here luckily they left us with a diagram which I can use to explain. We can prepare a salt such as copper to nitrate from dilute nitric acid and copper to carbon dioxide. Dilute nitric acid and copper to oxide forms to aqueous copper nitrate and aqueous to oxide, which filter and collect filtrate to produce aqueous copper to nitrate. And when you crystallize it and filter it to leave it alone and wash it with cold water to remove impurities, you're left with pure copper to nitrate crystal. And now we have preparing salts by reacting with an insoluble carbonate. Now here in this diagram, you use dilute hydrochloric acid and you mix it with magnesium powder, magnesium carbonate. Using carbon. We use the metals mixed in powder form and not in ribbon form, because powder reacts faster because it has higher sulfur, higher surface area. So when it's mixed together, aqueous magnesium chloride and magnesium carbonate is filtered and collected filtrate to produce aqueous magnesium chloride. So we crystallize, filter, and wash to remove impurities. We are left with pure magnesium chloride crystals. So how is insoluble salt prepared? By precipitation. Precipitation involves the mixing two solutions to form an insoluble solid that is separated out from the mixture. The general equation for precipitation of salt is aqueous solution AB and aqueous solution XY is mixed together to form insoluble salt AY and aqueous solution XB. To precipitate an insoluble salt AY, we can mix two aqueous solutions. AB contains the cation while XY contains the anion. When the two solutions are mixed, an insoluble salt AY and aqueous solution XB are formed. Salts can be prepared by starting the materials by filtration. So now we've made it to the end of chapter 12 of Igcse chemistry. Thank you guys so much for watching this video, and we have learned about oxides, acids, alkalines, and salts. I hope you've understand this video, and I really hope that you could learn a lot from this video. So please, when you're done watching this video, please answer 12 questions you can see in the Igcse chemistry textbook, or go to some websites and solve questions based on this chapter. If you don't find anything you don't understand, you can rewatch this video and learn and understand the chapter. Thank you guys so much for watching. Also, I should tell you that this chapter is also a very big chapter in the Igcse chemistry, and you should take it seriously when studying and preparing for your Igcse chemistry, as questions like this will appear a lot. So hit that like button and subscribe. Thank you so much for watching this video, and I'll see you all in the next video. Good day.